Well, we're done. We're ready. It moves. Let's do it like this. Okay. So we're going to solve the first problem, the first exercise. That is about the transfer function out of a differential equation. Silent, please. I'm recording. Thank you. Yeah. And here we have a differential equation. We need to express the transfer function in which y is the output and e the input. So what do we need to do? Yes, apply the Laplace transform to get into the Laplace domain, isolate the output, and get the ratio input-output. So you can proceed. So as a reminder, I'm going to give you this Laplace of the n derivative of t equals n s to the n times the Laplace transfer of the function. So based on that, so he's applying the formula term by term, the identity term by term. Yes, and now we're able to isolate the ratio y divided by e, because this is the transfer function. You see? Remember that we have input, no output divided by input. So we are interested in ys divided by es. This is what we want, not the other way. It's output divided by input. Very easy. No, we need only the function of s. We don't need to do anything else.
Yeah, but for factorize...
We don't need to factorize, yes. You can. The first question is the transfer function is a polynomial divided by the other polynomial in a way that it doesn't have to be factorized necessarily. We will need to factorize it to solve other questions. Well, thing is that we need to disappear these two and get only a function of s. So there is a problem in the notation there. The ratio, we want the ratio. So the function must be only in function of s. So these two must be at the other side of the equation. The ratio, you are able to see the ratio. With this information that is correct, you are able to get the ratio. It's extremely easy. But well, again, how difficult? Because actually, if you get this, like this, and you get this common factor, so here you have s squared plus s plus 2, yes or no? And if I want this, so I have to move this to this side, and this to this side. So y of x divided by x equals what? Yes. Be careful because be careful with the sense of what you are doing. Because if we have moved here, so we're moving to, this is multiplying, is going to, yeah, but now the sign of is like, well, it's okay, but not neat. It's okay. But normally we have to put this at this level. But it's okay. Okay. Yeah, more elegant. Okay, so you can put a square because you will need this information. So the second question is, let's verify who is the secretary today? Felix, as always, is it correct or not? Please do so. Second question, what is the impulse response of this system that has just been characterized? Yes, we have just obtained g of s, and the impulse response is just the anti-Laplace transform of the transfer function. For some reasons that... So now we're going to apply the anti-Laplace transform to this ratio of polynomials. So now you need to factorize. Now before was not necessary, now it's necessary. No, you are in the TP1. Now we're doing TP2. But here there is like a problem though, because there is something that when you apply the equation is 3. It is 3, so at the end you have a 3 here, so the factorization changes. So you will come today as well. Yes? So I have many volunteers. Julian, everyone, Felix, who else? I need the list, because here you are scarce. There is a scarcity. Matthew. He's not going to let me down. No. So I have enough people for today. And Thibault. So now what? We only have 2. No, we have 2 factors. Actually, this can be factorized. You don't need to complete the square. You can factorize the completion of the square is when we don't have more risks, but you can factorize this. This is completion of the square, I think. It's factorization. You can solve even simpler. You can factorize this easily by inspection without applying this formula of the second degree. Do you or not? How do you say it? I know that this is a technique, but when the polynomial, it cannot be factorized, and it was to be. By inspection can be solved. You don't need to. It would be. Yeah. 2. Yeah. So you don't need to complete the square. Yes. And now you do the partial fraction decompositions. It's S. I know you like the X. But don't get, well, if you don't get confused, it's okay. Yes. Now you have to do the partial fraction decomposition of this. Of S. And it's uppercase S. Normally, by convention, it's uppercase S, but you can use them the lowercase.
It's just for not confusing
with a 5. Yes, okay. It's valid. But how do you know that it's 1 and 1? So you have 2. Ah, okay, yes, we have to solve. I thought you were a guesser. So do what you know. Your name?
Oriane.
Oriane. And Mathilde. I remember. Okay, now you have expanded and you are able to use the table. If you don't know it by heart, I brought mine. I can allow you to use if needed. If you remember, just do it. Yes, but remember that here the A, so don't put it in terms of A, put it in as a result of the expression that you have. It's minus though, because you have to invert. No, I don't know by heart, but yes, when you have positive, you have negative, and you have to multiply by the step function by convention. Is it correct, Felix? You are following up. So the idea is that someone's here and the others are verifying. Or you must be doing the exercise, no? Yeah? You should. Because it's not for the others to sleep and only one person to work. It's for everyone to participate. So this answer is correct. And we can even expand a question that is not asked here. Yeah? Yeah? That is not asked in this very tip D, but is about the stability of the system. Can we say that this system is stable or not? We have two options, yes. The option in the time domain and the option in the Laplace domain. But, well, you can choose either one and tell me. In the time domain, is the limit as t approaches infinity, the function must approach 0. So there shouldn't be any trace of this input, which it does because these two exponential decay evaluated in infinity approaches 0. So the system is stable. But at looking at the Laplace domain, we can see that the poles, the real part of the poles are negative. Because it's -1 the solution and -2, the two are negative, and as a result, we can say that the system is stable. Just a reminder of what we saw on Monday. Second question is, well, third, in fact. It asks what would be the output if the input is a sinusoidal function of 1 radian per second and amplitude equals 2. So, no, orally, just, we want to know the output, because we have actually you erased, okay, here. We want to know, we have just obtained G. Yeah? G. And we want to know the output. And they are giving us this, the input. The input is the input in terms of T. G of T is, will be able to assemble orally a sinusoid of a frequency of 1 second and an amplitude equal to 2. So what is this function of T? Well, it's 1. 1 radian per second is 1 divided by second, because radian means numerically nothing, so it's a-dimensional. So a sample, yeah, that's it. And now with this, we want, you can isolate again what would be the output. It would be multiplying the input times. Actually, we see la sortie. Actually, we have there, we have here, we have is, because they said the other part is E, and this part. This is the input. The exercise says input and one's output, and the other is the other way around. Okay, so you can start. You can continue.
So now we do the Laplace transform of.
But remember, you want the output, so move this here, so you will be able to write that G of S equals G, it's Y of S and E of S. You have this, and you can calculate this. But it's E, no, but it's E of S is the Laplace transfer of this. You have to. So do it. What is the Laplace transform of 2? No. You should see the table, maybe, because it's not that. It's the Laplace transfer of. We don't use the U when we go to the Laplace domain, the U of t. We use the U when we return from the Laplace domain. Yeah? Yeah.
Something like that.
Well, I invite you to see the table yourself, because you must be handy. Well, yes, I think so. Let me see. If I were you, I would inspect. I wouldn't rely, because the table is very extensive. So what is that? That is omega divided by S squared plus omega squared. This is, what is that? But yeah. So what is omega? So yes. So put it. Yeah. A square. No, a square remains a square. A square remains a square, and omega squared is 1. So you have obtained, and here you can put these two here. And now you have this, because you did it, and this one have just obtained. And now you calculate y of e, y of x. Here. Yeah. And now you have y of x, and what we want to do, what we want to obtain is y of t, because this is the question. What is the function, the output in time of this? This is no longer, this is just one. This one becomes only one thing, divided by 2. So this is a new anti-Laplace transfer to solve. It's not the product of the anti-Laplace transfer, because you have you know for this, but when you multiply, you have to combine all of the parts and solve the problem from 0. Yes? So what do you have to do there? Factorize. The factorization is the same, so factorize, but the partial fraction expansion is not the same. It's trickier. Yeah. So the technique is not as easy as this one. So can you write it down, please? What would be in terms of? We're not going to solve it because it's complex, but at least just state the. So that is correct. Also correct. And incorrect.
Okay.
Yeah, no, the problem was not there. Remember, yes, that the variable is S. The variable is S.
Yes.
So if you continue like that, you can make an error. That is correct, but since this is very laborious, so I'm going to allow you to copy directly the answer of that, which is this line. Don't solve because it's going to take ages to do that. Yes, you can copy that to continue, and after the answer of last transfer, you don't copy. Maybe you can continue here because we have more space. There, starting there. Okay, and now you can apply, if as a matter of your preference, table. If you want by heart the formulas, my table is available here. If you want to use it.
I can try.
I don't know.
There's an error.
Error, please check.
3/10 S of S squared plus 1. C'est 3 dixièmes de S sur S carré plus 1.
Là, here?
Ouais.
You are, I forgot. Justin. Lucien. They're similar names. Justin, Lucien. They rhyme. You can make a poem. I don't know. It's for you to tell me. I have a table I can allow you to use. Okay. Okay, you can continue with the table. You got the better mark, by the way. It was confirmed for the two groups. One asked me who got the best. I said, well, it was everyone. 16.5, including the participation, but it's very well deserved because you have to work a lot. You know, as you think, you have to fill at least 5 whiteboards to get something, so it's not for free. What's the matter here?
This term is not right.
No, because it's either cosine. Yes, when you see it, one is cosine and the other is sine. But there is no yes. Let me see. Here, man, you are not looking at the right entry of the table. This is Laplace transfer, which you are not doing. You are doing anti-Laplace properties and inverse Laplace transfer. And here, let's expect that here, this one has this shape. 1 divided by s squared, but something squared, because there is 1 square here. And here you have s divided by s squared plus something squared. So at the end, how about this, Felix? Is that correct?
Un tiers, un cinquième, de monter de. Ouais, c'est ça. Ouais, c'est bon.
Is it correct? Okay. Well, let me stop my recording because I think I have enough material.